Welcome back. And we're back in chapter 21. Let's bring this to a close here when we discuss the reactivity of amides and also nitriles. And I have a few comments here on thioesters, which we might come across actually we already did come, maybe not thioesters, but we came across acyl phosphates in the chapter on lipids when we were talking about phospholipids and things like that. And compounds like this might also come into effect when we talk about carbohydrates. Unfortunately, we will need to skip chapter 29 when we would certainly have run into both thioesters and acyl phosphates as we went over metabolism. But given the nature of, given the extraordinary nature of this semester and everything being online, we needed to cut some material, so that's what we're going to cut. Good, but of course, those who are interested in that topic can feel free to check out my chapter 29 class notes, which I will leave online, but I will not examine you guys in chapter 29 on either of the remaining hour exams or on the final exam. So same thing with chapter 20. So we will cover, though, chapter 31, which is on polymers. I feel that those of you who are engineering and material science majors deserve that at the very least, because you've been very patient through a lot of biochem-related material. Good. So amides in many ways are kind of similar to esters. They're a little bit less reactive also. Amides can also be hydrolyzed, just like esters, under either acidic or alkaline conditions. The mechanisms are very similar. But the great thing is, we're also going to get in just a few minutes to the hydrolysis of nitriles, which can also occur in either alkaline or acidic conditions. And you'll find a nice surprise when we look at the nitrile hydrolysis mechanisms, both in acidic solution and in alkaline solution, because at some point along the way of both, you essentially wind up with an amide. So the nitrile turns first into an amide and then goes to the carboxylic acid. The idea being that if you know the nitrile hydrolysis mechanisms, you automatically get amide hydrolysis thrown in for free. And it makes it quite a bit more efficient. So I think you'll see that in just a few moments. Chapter 29 mentions step growth polymers, which is something that we'll cover in chapter 31. So we're going to basically postpone this until then. But the idea behind them, we can already understand. We already know that you can take an acid chloride and treat it with an alcohol, that is, alcoholize the acid chloride and get an ester. Well, what if you played a trick on the system by taking some molecule that's a diacid chloride, which thousands exist? You know, you could have something like, and if I think about it, I should be able to tell you the name of this diacid chloride. What's the mnemonic device for the diacids? Oh my, such good apple pie, sweet as sugar, oxalic, maleic, succinic. So this will be succinyl chloride because it is 3 carbons. Not that I really care if you know that, but that mnemonic device with the first letters of the names of each of them, oh my, such good apple pie, sweet as sugar, is kind of amusing. So in any case, this is a good example of a diacid chloride. What if we now treated this with a diol? Like, oh, I don't know, how about propane diol, propane 1,3-diol, and thousands of other diols exist also. Well, this OH group can react with this acid chloride and make an ester. Meanwhile, the OH group on this side can find another molecule of this diacid chloride and make another ester. And this and then this acid chloride will find another alcohol to react with, and on and on and on and on and on. You just get this long chain. So it's one way of making a polymer. The resulting polymer you'd get here would be called a polyester, which I think you've heard of those. And you could do something very similar with a diamine to make a nylon or a polyamide. So we'll postpone the rest of that for now, but I just want to point out the idea behind it is something we understand already quite well. Good. So that being said, let's tackle the final capstone on this chapter, so to speak, and consider the hydrolysis of both nitriles and then amides thrown in for free in both acidic medium and alkaline medium. And I think you'll find there's a lot of similarities to the reactions we looked at with carbonyl groups, because really the nitrile group is very similar to a carbonyl group in terms of reactivity. Actually, I think we can now close this. I don't think we need that anymore. I can now open this up so that it covers more of the screen and we can see it more easily. So just as the first step of an acidic solution mechanism with a carbonyl compound is protonating that carbonyl oxygen, so the same thing here. The first step is going to be protonating the nitrile nitrogen. All we have present, remember, is dilute aqueous acid. This generally does require heat as well. So this protonated derivative is now even more electrophilic and susceptible to nucleophilic attack by even a moderate nucleophile like water. This species that we get here is now ripe for some proton transfers, very typical in acidic medium. We need to be careful that we show them correctly. So water, of course, is going to be our base. Remember, water is always present when you see H3O+. And admittedly, the textbook and OWL are both sometimes a little sloppy. They will write H3O+, comma, H2O. I feel that's redundant. H3O+ implies that water is present. So that's what we'll use to pull off this proton. And then this species actually is resonance stabilized. You could also have a double bond here with a plus charge in oxygen and a single bond here with a minus charge in nitrogen. That's going to be the minor contributor. But you could draw it either way since it's a resonance stabilized species. Using this resonance form, we can now show this electron pair coming in, this lone pair in oxygen coming in to form a carbon-oxygen pi bond, and then we break the carbon-nitrogen pi bond, and this arrow here means that this proton's going to wind up on the nitrogen. So, but that's not the only correct way to draw that step. Remember the rules for resonance stabilized species. We'll see the same thing in the alkaline case. Remember that it's always possible to draw a correct mechanism using any resonance form, any of the resonance hybrids you like. So once we have this, lo and behold, take a look at that structure. It's an amide protonated. And so that's why this will include the mechanism of the acid hydrolysis of benzamide, because the first step of benzamide would be to put the proton in the carbonyl oxygen, just like always. So that's why if you understand the mechanism of the nitrile hydrolysis, you automatically also understand the mechanism of amide hydrolysis. And so since our oxygen is protonated, we can go ahead with nucleophilic attack using a water molecule. Again, not a hydroxide ion, we're an acidic medium. And so that gives us this intermediate. Unsurprising that we will now need to do a few more proton transfers. They will both be intermolecular and will be in such a way so as to avoid getting an intermediate with a +2 charge. We always want to try for intermediates with no charge or a +1 charge. So that's why we pull this proton off first using a water molecule. And then we protonate our nitrogen so we can lose the nitrogen as a leaving group in a molecule of ammonia, which we will generate. In fact, that's the next step. We kick out ammonia as a leaving group, not an H2-. That would be an impossible leaving group in acidic medium. Alkaline medium, maybe. And in fact, we'll see that happening in just a moment when we do the alkaline solution mechanism. And of course, we can have a lone pair and this OH oxygen help. It doesn't matter which one, those two OHs are the same. So now we have our carboxylic acid with the oxygen of the carbonyl protonated. We simply use a water molecule to pull that proton off, and we get our free carboxylic acid. And again, why do we use a water molecule instead of the ammonia molecule? Well, the answer is because we do generate ammonia. That's true. But we just get 1 mole equivalent of ammonia floating around in this giant ocean of water, actually acidic water. So most likely what's going to happen to our ammonia molecule is it'll get protonated again to form the ammonium ion, NH4+. But there's either way, there's not going to be enough of it to affect the course of the reaction. So again, our water pulls off our proton here, and we're done. We've hydrolyzed our nitrile or our amide and formed a carboxylic acid. Okay, so now we're in pretty good shape. Let's try to make that a little bit bigger so we can see it a little better. Okay, so let's do the same thing. Instead of benzamide, I'm using or benzonitrile, I'm using pentane nitrile. And let's consider treating this with aqueous potassium hydroxide. And so our hydroxide ion will attack our nitrile carbon directly. And so we will get the resulting anion, which is an anion, but again, being an acidic solution, I think we can rationalize this. I think we're okay. I imagine that would get protonated pretty quickly using a water molecule. Of course, there's water present as well as the hydroxide ion. Of course, I could just as easily have used lithium or sodium hydroxide. That gives us this species over here. It's actually kind of like a carboxylic acid. That means this proton over here is going to be pretty acidic. It'd be pulled off very quickly by the hydroxide ion, which is present in several times in excess, several mole equivalents. And we can then do a very similar step as we had before. This also is a resonance stabilized species. We could have a carbon-oxygen double bond and a carbon-nitrogen single bond with the minus charge on nitrogen. You can certainly draw it that way too. That being said, what do we get after we've done that? Hey presto, it's an amide. And so we've just in a few steps gone from a nitrile to an amide. So that's why if you understand alkaline hydrolysis of a nitrile, you automatically get alkaline hydrolysis of an amide thrown in for free. You would simply start in the middle and you'll know what you need to do based on what you're given in terms of the question. But if you're asked to hydrolyze an amide, you would just start here or at the equivalent. It may not be this exact amide, but it would certainly be an amide. And by the way, oh, never mind. By the way, nothing. So we'll just go on. This species, again, we need to consider relative pKa's. This species is reasonable over here with that minus charge in nitrogen. But to put a minus charge on NH2 and make NH2 minus as a leaving group, it's kind of pushing it, I have to admit. It's maybe even a little over the edge. But when we consider the pKa of ammonium nitrogens, they are very much they're very much less acidic than nitrogens like this with or nitrile nitrogens with a plus charge. So that's why we're not protonating this nitrogen first. The pKa of that species would be about -10, but we do protonate this nitrogen. The pKa of the resulting ammonium ion is about 10, 9 or 10 usually. And if we're at a pH of 14, that's reasonable to invoke a species like this. So don't just memorize it. We need to understand why the species that are present in our mechanism are there. Either way, we will quickly lose a molecule of ammonia. We'll form our carboxylic acid, and then just like before, our base will very quickly deprotonate our carboxylic acid. There's no way to stop that. All of this happens in the same alkaline solution. So that's, again, we have a numbered synthesis, so to speak. We'll treat the nitrile, we'll dissolve it in aqueous base, and everything that can happen in base will happen until everything's done reacting. And so only until there's no more nitrile molecules and all of them have reacted and we're just left with this carboxylate ion, again, floating around quite happily in our aqueous basic solution, then we will add our aqueous acid to work up the reaction. The aqueous acid will first neutralize any leftover hydroxide, And then we'll start putting the proton back on the carboxylate to generate our free carboxylic acid. So mechanism looks somewhat different in alkaline solution, but the key to understanding why we write what we do is by having at least some degree of an understanding of relative pKa's of this nitrogen, which is a horrible base, as opposed to this nitrogen, which is a fairly decent base, actually. And so it's the difference between having if we protonated this nitrogen, NH+, you'd have a species with a pKa of about -10. There's no way you're going to make that in an alkaline solution. You're 20 orders of magnitude too acidic. However, when we protonate this nitrogen, now our pKa is probably around 9 or 10. So we're only a few orders of magnitude away from pH 14. You generally don't want to invoke species that are further apart than about 7 or 8 pKa units at the very most. And since we're away by maybe 3 or 4 pKa units, we are good to go. So take a look at that. And other than that, that's basically it. So thanks for stopping in. And we will continue on with chapter 26 later. Until then, have a good day.